This is section 11.4, areas of regular polygons. Remember, a regular polygon is any polygon that is both equiangular and equilateral. So all the sides are the same length and all the angles on the inside are all equal. Well, in any circle, we can inscribe a regular polygon of any number of sides. You give me a number of sides, I can inscribe inside of a circle a regular polygon with that number of sides. I've got 3 drawn here for you. If I wanted to inscribe a square inside of a circle, the way I would do it is I would start at the center of the circle and I'd draw 4 90-degree central angles. It's going to guarantee that the 4 points where those angles meet the circle are going to be the vertices of a square. If I want a regular hexagon, a 6-sided polygon, I draw 6 60-degree central angles. Why 60 degrees? Well, because remember the way I figure out the measure of each interior angle is to take n minus 2 times 180. So if I want a hexagon, I'm going to do 6 minus 2 times 180, which is 4 times 180. And what is 4 times 180? 720. If I divide that by 6 to get each one is 120 degrees. So total was 720 and divide that by 6, I get 120. That means I want each angle to be 120. So if I divide that in half, I'm going to want 60 degrees. Same thing for a decagon. I'm going to draw 10 36-degree central angles. So the process exists for drawing any regular polygon with any number of sides inside of a circle. Similarly, around any regular polygon we can circumscribe a circle. If I start with a polygon, I can draw a circle around it so that the vertices of the polygon are all points on the circle on the inside, and all the sides of the polygon are chords of the circle. So with that, we have some definitions. The center of a regular polygon is the center of the circumscribed circle. So the way we define and find the center of a regular polygon is to find the center of the circle circumscribed about it. So I've drawn a hexagon on the right here. The center of the circle is O, so the center of the hexagon is O. The radius of a regular polygon is the distance from the center to a vertex. In other words, it's the radius of the circle circumscribed about it. The distance from the center to a vertex, like that distance, would be the radius of the polygon. Because it's the distance from the center to the vertex, it's also a radius of the circle. A central angle of a regular polygon is an angle formed by 2 radii drawn to consecutive vertices. So I've drawn one radius to a vertex. If I draw another one to a consecutive vertex, like this one, then I'm forming a central angle of the polygon, which is also a central angle of the circumscribed circle. But here we're interested in the polygon, so we define that to be a central angle of the polygon. An angle whose vertex is the center of the polygon and whose sides extend from the center to vertices of the polygon, consecutive vertices. The apothem of a regular polygon is the perpendicular distance from the center of the polygon to a side. Perpendicular is in parentheses because, remember, the way we find the distance between a point and a line is to take the length of the perpendicular segment. So we really don't need to say that. That's the way we define distance, but a reminder that we find it by taking the perpendicular. So if I take the distance from the center to a side, so if I want the center to this side down here, I'm going to draw the perpendicular segment from the center to that side. It's going to be a right angle because it's perpendicular, and that is the apothem, which we'll call A. Notice there are, for a hexagon, 6 apothems. I can draw one there, 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 and I can draw one there. The length of all 6 of those are all going to be the same because it is a regular hexagon. So apothem is really a new word. of this section. With that, we can find the area of a regular polygon, any polygon, that as long as it's regular, so equilateral and equiangular. The area of a regular polygon is equal to half the product of the apothem and the perimeter. Perimeter is the distance all the way around. If I know the perimeter and the apothem, I can find the area. Or if I know just one side and the apothem, I can find the area, because with that one side, I can find the perimeter, because all the sides are equal. So I can just multiply that side by the number of sides that there are, and I'll have the perimeter. So we have this formula. The area is 1/2 A times P, where A is the apothem, P is the perimeter. Now why? That seems like a rather random formula. Why the A and the P, and why the 1/2? Well, it all goes back to the area of a triangle. And to illustrate it, I could use just this hexagon here, but this will work with any regular polygon. In my hexagon, I can draw 6 triangles on the inside that are all going to be congruent, because this is a regular polygon, so all the sides are equal, the central angles are equal, the radii are equal. So I've got easily 6 congruent triangles, and exactly 6, because there are 6 sides. Each of these triangles we can find the area of. So if I want to find the area of this triangle that I'm working with here on the right, how do we find the area of a triangle? What's that formula? 1/2 of the base times the height, right? 1/2 of the base times the altitude. Here, the area of that triangle is going to be 1/2. The base is the side of the hexagon, which I've labeled as S, and the height, or the altitude, is the apothem A. So that's just one triangle. How many of them are there? There are 6. So if I want the area of the hexagon, I'm going to take 6 times 1/2 of S times A. Well, multiplication is commutative. I can rearrange the order of things here. So I can say that's 1/2 of A times 6S. S is the length of a side, so 6 times S is going to be the perimeter, because there are 6 sides. And that's exactly where we get the formula. Now I could do that with any regular polygon. I illustrated it with a hexagon, but the process would be the same for any polygon. So that's our formula for the area of any regular polygon. So let's use that. Examples. Find the area of a regular hexagon with an apothem of 9. So I've given you the apothem, but I have not given you the perimeter, and I have not given you the side with which you could find the perimeter. So we're going to have to find that. And the fact that it's a hexagon makes it useful, because in a hexagon, as I said and calculated earlier, the area of one interior angle is 120 degrees. So the area of half of it is 60. That means that this angle here is 60 degrees. The area of a central angle in a hexagon is also 60 degrees. Means half of that is 30. So that means I've got a 30, 60, 90 triangle. Let me redraw it here, where the apothem is the side opposite the 60-degree angle in this case. If I need to know the side length of the hexagon, I'm going to find this side. Let's call it X. That will be here. I'm going to double that and get the length of a side, and multiply that by 6 to get the perimeter. Okay, so let's remember the ratio, 1 to radical 3 to 2. I've got 9, which is the side opposite the 60-degree angle, so that goes in the middle. I need to know the side opposite the 30-degree angle, so that's my X. That's what I'm going to try to find. What do I do? If I have the middle, I want to find the one on the left, I divide by radical 3. But dividing by radical 3 means I have to get rid of that radical on the bottom. I get 9 radical 3 over 3, or just 3 radical 3. So that is the, that's X. 3 radical 3. So the length of a side is going to be 2 times x, or 2 times 3 radical 3, or 6 radical 3. The perimeter, since it's a hexagon, is going to be 6 times length of a side, or 6 times 6 radical 3, which is 36 radical 3. And now we're ready to apply the formula, because now we know everything we need to know. So the area, 1/2 of A times P, the apothem times the perimeter. The apothem, we're told, was 9, so 1/2 of 9 times perimeter, which is 36 radical 3. Don't go to a decimal, I want the radical 3 in there. And I remember that multiplication is commutative, so I can take the 1/2 times the 36, which gives me 18, and the 18 times 9 gives me 162 times radical 3. That's the way I want your answer. I don't want a decimal. Number 2, find the area of a regular polygon with 9 sides, otherwise known as a nonagon, inscribed in a circle with a radius of 10. So I've got 9 sides, and I've got a radius of 10. So in order to find the area, I need to know the apothem and the perimeter. In order to find the perimeter, all I have to know is the side. So if I can find the apothem and the length of a side, I'll be able to find the area. All I know is the radius, and I know there are 9 sides. Well, let's find the measure of this angle AOB at the top. The measure of angle AOB, the whole circle is 360 degrees. So angle AOB is going to be 1/9 of the whole circle. Because there are 9 sides, there will be 9 central angles, so I'll take 360 divided by 9. 360 divided by 9 is 40. So the central angle is 40. That means angle AOX is 40 over 2. It's half of that, so 20. And I end up with a triangle like this, 20 degrees there. It's a right triangle, so that means this has to be 70 degrees down here. I've got 10 on the hypotenuse, and I want to know A, and let's call that X, where X is half of S, the side length. So I've just redrawn this triangle over here. Okay. Now I'm going to use that triangle and not triangle AOB because I want a right triangle, because I can do stuff with a right triangle. So if it's not a right triangle, I really can't do much with it. What I'm going to do with it, since it's not a 30-60-90 triangle or 45-45-90 triangle, is I'm going to have to use some trig. So I'm going to say, if I want to find, say, x, I know the hypotenuse, so I'm going to use either sine or cosine. If I'm going to find x, one way I could do it is to use the sine of 20 degrees and say that that is x over 10, the opposite over the hypotenuse. So x is going to be 10 times the sine of 20 degrees. So let's find the sine of 20 degrees and multiply it by 10. My handy calculator here. Sine of 20 degrees times 10 is about 3.42. So that means that S, the side, is going to be 2 times 3.42. This is approximate. And that is equal to 6.84. So that's our S, 6.84. Now I need to find A. A, we can use the 70 degrees in cosine. I'm sorry, 70 degrees in sine or the 20 degrees in cosine, either way. Let's say we use the sine of 70 degrees. Let me do this in a different color. The sine of 70 degrees equals A over 10, the opposite of the hypotenuse. So A is going to be 10 times the sine of 70 degrees. Again, I just go to my calculator and do 10 times the sine of 70 degrees, and I get 9.397 approximately. Okay, so now I know A and I know the side. So the perimeter, P, is going to be 9, because it's a 9-sided polygon, times the length of the side, 6.84. So that is approximately, let me do it on here, 9 times 6.84, 61.56. And the area then equals 1/2 the apothem times the perimeter. 1/2 9.397 times 61.56. So that's all approximate. That would be $289.2. So a lot we have to do to find the area of that, but the point is we can do it, and we know everything we need to know in order to do it because we now know trig. And I can apply the same process to a polygon of any number of sides. Number 3, find the perimeter and area of a regular octagon with side 5 and apothem A. So it's an octagon, 8 sides. So the perimeter is going to be 8 times the length of the side, which is 5. So the perimeter is going to be 40. The area is going to be 1/2 of the apothem times the perimeter, or 1/2 of A, the apothem, times the perimeter, 40. Remember, multiplication is commutative, so I can take the 1/2 times the 40 right away and get 20 times A. So the perimeter is 40, the area is 20A. Your immediate practice problems. Number 1, find the area of a regular hexagon with apothem of 5 that's exactly like example number 1. Number 2, find the perimeter and area of a regular decagon with side 6 and apothem A that's exactly like example number 3. So see example 3, see example 1. And that is the end of section 11.4.